Hello, everyone. Thanks so much for the nice introduction. And today I'm going to talk about a project that we have worked for like more than 1 year. It's about efficiently verifiable quantum advantage on near-term analog quantum simulators. So what is demonstration of quantum advantage? From my understanding, it's a game between a classical verifier and an untrusted self-claimed quantum prover. And the goal of the game of the prover is that the prover wants to prove to the verifier that he indeed has some quantum computational power. And the goal of the verifier is to accept only if the prover indeed has some quantum computational power. So there are some very simple ideas of doing demonstration of quantum advantage, like we can do factoring problem. This is very simple. The verifier just sends a large integer to the prover, and the prover, if the prover can factorize it in a very short, reasonable time and report it back to the verifier, then of course the prover would have some computational power beyond what we have currently. However, this idea is not very near-term feasible because to run a large source algorithm, we need some very good quantum devices. There are some other ideas like the cryptographic proof of quantumness, which is basically a test that can only be passed by evaluating a cryptographic function in superposition. So this is easier to implement than Shor's algorithm, but still this is unfortunately not very near-term feasible. The third idea is very popular. It's based on random circuit sampling. So basically, the basic fact is that the measurement outcomes from some random circuit samplings are from a classical Hart distribution. So this idea has been experimentally realized, so we know it's much easier than the first two. But unfortunately, it is very inefficient to verify or benchmark the samplings. Therefore, it seems to us that it's quite hard to have a demonstration of quantum advantage that has all of these good features under this framework. So we think about taking a step back and change the rules of the game a little bit to give the prover a little bit of trust, say with trusted measurements. So to have a taste of what trusted measurement means and why it's useful, let's see an example of a classically hard IQP sampling problem. So this problem, the hardness of this problem is first proved in this Bermeo-Vega et al. Paper and somehow reinforced in this Ringbauer et al. Paper. So the setting of this problem is that we have n qubits. They are on a 2D square lattice. The initial state of the system is phi naught, denoted by phi naught. And in this state, it's a product state. Every qubit in the state is randomly sampled from a plus state or a plus state with a fixed relative phase between the 0 and 1, which is pi/4. And it supports some Hamiltonian evolution, which is a ZZ plus Z nearest neighbor uniform Hamiltonian. So it's quite a simple Hamiltonian. It's just the sum of the, where this NN denotes nearest neighbor, the sum of this ZI/ZG terms and ZI terms, and all coefficients are just pi/4. So the result of these two papers is that if we let P be the distribution of X basis measurement outcomes on the state that is e to the minus IH, the unit time Hamiltonian evolution defined by ZZ plus Z, acting on the input state phi naught, then sampling from the P distribution within some constant total variation distance is hard for classical computation under some plausible computational assumptions. This is a very straightforward corollary of this result. That is, if the noise rate in measurements is known to be tiny, and is known, then if the state, that is e to the minus IH acting on phi naught, is prepared with fidelity higher than some threshold, then we can also say quantum advantage exists in this state, because obviously by measuring this state, we can generate samples from the Hart distribution. Okay, so now why we need trust measurements? Why we need to trust measurements? We can see that a very simple scheme of demonstration of quantum advantage can be built based on this problem. So basically, the verifier just asks the prover to prepare the output state, and the prover needs to measure the output state in the X basis and report the measurement outcomes back to the verifier. However, it turns out that in this case, the verifier needs to verify whether these samples are from this Hart distribution, which is generally quite hard because it takes exponential time to verify if they are from the distribution. So this is actually the same problem as the quantum supremacy experiments. Or we can check the fidelity of the output state, as we mentioned in the last slide. Well, unfortunately, this is also inefficient or impractical if only classical communication is allowed, and if we need to do this in a secure manner, meaning that we don't want the prover to cheat. We need to see when they are cheating so that we can rule out this case. So in order to do this verification in an efficient and secure manner, we need to somehow relax some game rules. So here, a commonly used model in computer science is that they allow the verifier to measure the state by herself. But in this case, the quantum state needs to be transmitted from the prover to the verifier, which is pretty difficult in the near term, especially when there are many qubits in the state. Therefore, we want to think about some equivalent scheme of this state transmission, which is the scheme that the verifier trusts the prover for measuring every prepared state in the basis given by the verifier with noise rate lower than some threshold. So we call this scheme a trusted measurement scheme or trusted measurement assumption. So we can see that this trusted measurement actually contains two parts. The first part is state commitment, meaning that the prover must first prepare the states and then receive the instructions and then prepare and the measurement and then measure each copy as instructed by prover, instead of first receiving the instructions and preparing whatever state they like to cheat us. The second part is that the measurements must be performed honestly and correctly. So actually, the Bermeo-Wagner et al. Paper already gives a verifiable quantum advantage scheme based on this problem in the state transformation or trusted measurement scheme. But in their scheme, the drawback is that quite a few samples are required. So the prover need to prepare many copies, and the number of copies will increase as the system size increases. So in this work, we propose a quantum advantage demonstration protocol that is based on the same sampling problem in Bermeo-Wagner et al. Paper as we introduced before at the beginning. And we claim, and this protocol requires either trusted measurements or quantum state transformation. We also claim that our protocol achieves a reasonable balance between three nice features. Well, we don't claim that we're the best in any of them, but we think it's a reasonable balance. The first is rigorous hardness guarantee. We have that because we're based on the same problem as the Bermeo-Wagner et al. Paper. And the second is efficient verifiability, meaning that the verifier only need to perform polynomial time classical computation, and the prover only need to prepare constant copies of the state. We call that constant sample complexity. And finally, we claim that we have some kind of near-term practicality, because in this case, the prover need to be able to perform some quantum capability called mostly analog commuting plus global CZ, which is, of course, harder than just analog commuting Hamiltonian simulation, but we claim that this is not too hard to implement in the near term. So this protocol, the paper and the talk has two parts. The first part is the verification protocol, which is basically the verifier's strategy. And the second part is the experiment proposal, which is basically what the prover need to do in the protocol. All right, so let's start by the verification protocol. Let's first have an overview of the protocol. The first step is the verifier needs to send some classical information to the prover. And this classical information contains two parts. The first part is the classical description of the input state, which is find out, which is exactly the same state as we described in the beginning, that random state, random product state. And the second part is the instructions of measurements, which is what the prover need to do in this trusted measurement scheme. And we will explain these measurements later soon. And we'll know that some measurements are for verification purpose and some others are for sampling. So the first step of the verifier is an untrusted step. So in this step, the first step of the prover is untrusted step. So in this step, the prover needs to prepare NM copies of a state called a single step history state. So here NM is constant, meaning that it's independent of the system size or the number of qubits. And the history state here plays a key role in our efficient verification scheme. And the history state is defined as the superposition of the input state, which is phi naught, and the output state, which is e to the minus ih, the unit time zz plus z Hamiltonian evolution acting on the phi naught state. And these two states are correlated with one more qubit that is in the front, which is called the clock qubit. And if it's the input state, the qubit will be in 0 state. And if it's the output state, the qubit will be in the 1 state. And recall that here, the h, the Hamiltonian, is just our zz plus z Hamiltonian introduced in the beginning. Okay, the second step of the prover is a trusted step. where the prover needs to measure every copy as instructed by the verifier and reports measurement outcomes to the verifier. Finally, the last step, the verifier needs to calculate a lower bound of the output fidelity, which is f out. Note that here this f out is not the fidelity of the history state, but the fidelity of the output part of the history state, which is the fidelity of the e to the minus ih acting on phi naught part. And she needs to compare that against the threshold fidelity. Okay, so now let's see why this history state is useful and how we can use it to do the verification. The intuition of using the history state is that compared to just being given the output state, which is this one, the history state allows us to check the initial state preparation and Hamiltonian evolution separately and independently, which enables more efficient verification. All right, so let's look at the real state that may be given by the untrusted prover. We know that prover is untrusted, so he might be giving any arbitrary states. And here we are just focusing on the example of pure states. Actually, our result will also apply to mixed states. And so let's see, this is actually the most general model of a pure state of n+1 qubits, where alpha and beta are just random, just arbitrary complex numbers, and phi in and phi out are just arbitrary n-qubit states. Remember that ideally we want the phi in, the input state, to be the same as phi naught, which is the ideal input state, which is that random product state. So we call this part is actually about input state preparation. And we want the output state to be exactly the in time Hamiltonian evolution acting on the input state. So we call this part about Hamiltonian evolution. So we can easily see that if both conditions are satisfied, the output fidelity will just be 1. So this gives us the idea of doing verification. We just need to check the input fidelity and evolution fidelity independently and, well, separately. So to check the input fidelity, which is the overlap between the phi naught and the phi in state, that's quite easy. We just measure the clock qubit first, and if it is in state 0, then we measure all other qubits, because we know that phi naught is a product state. It's quite easy to check whether they're the same. Just do the measurement qubit by qubit. And the evolution fidelity, which is the fidelity between the phi out state and e to the minus ih acting on the phi in state, is obviously harder to check. So I'm not going to introduce the Feynman-Kitaev Hamiltonian here, but we did get some inspiration from this very famous encoding. So we need to consider an operator that is called O10 that has 10 in the clock qubit and has e to the minus ih in the system qubits or simulator qubits. So we find that the expectation value of this operator is quite useful. The expectation value is equal to alpha squared times beta squared times the evolution fidelity. So that if this expectation value of O10 is estimated to be higher than some threshold, we know that the evolution fidelity is higher than some threshold. Now the problem is, how can we measure the value of O10, or how can we estimate its value? We noted that O10 is obviously not a Hermitian. But fortunately, its de facto value can be easily estimated for our h, because in our case, the h is just zz plus z. It's a commuting Hamiltonian. So first, the 10 part acting on the clock qubit is just proportional to x minus iy. So we just measure like half of the copies of the history state of the state given by the prover in the x basis and the other half in the y basis. The hardest part is obviously the measurement of e to the minus ih. Well, due to the commuting nature of our Hamiltonian, which is just zz plus z, we have really nice formula for e to the minus ih. It will just be the product of I plus zk times the product for I plus zj. So this means that to get the value of e to the minus ih for any single copy of the state given by the prover, we just need to measure every system qubit or simulator qubit in the z basis. So get the zi values, and plugging these values into this formula, we will get the value of e to the minus ih, which is, of course, a complex number. So this means that we only need like On times of complex number multiplication, which is like linear time classical verification. It's quite efficient to estimate the evolution fidelity. Okay, so yeah, one major result of our work is that we derived this formula for the lower bound of the output fidelity, which is 16 times the O10 squared, the expectation value of O10 measurement, and the 3 times the input fidelity minus 6. Plus some higher order terms that are some details. And so to do the verification, the verifier need to get these values, 010 values, and find out overlap values from the prover, and need to calculate the lower bound of f out to a constant precision, because she needs to compare the f out to some threshold values, which is also constant. So it suffices to just estimate both parameters, this 010 squared and find out phi in overlap squared to a constant precision. And this can be done by measuring constant many copies of the states. And this is something that can be easily shown by applying Hopf inequality, because all the observables in our protocol are like bounded. So let me give a summary of this protocol, this verifier's part. This protocol is actually quite simple. The prover needs to prepare a history state, and the verifier needs to estimate the input and the evolution fidelities through trusted measurements to lower bound the output fidelity. And the verifier only needs to run polynomial time classical computation, and we have constant sample complexity because only constant number of copies of the state, which is the history state, need to be prepared by the prover. Now, let's move on to the second part. It's about prover strategy. So what does the prover need to do is actually just preparation of the history state, which is something quite non-trivial to do. Let's consider this task by starting from an easy to prepare initial state that is just plotting the first qubit and find out the ideal input state in the simulator qubits. And now it seems like if we want to go from initial state to the history state, we need to perform some controlled Hamiltonian evolution, which is pretty hard because the Hamiltonian itself is two-body. Controlled Hamiltonian evolution will be three-body. That is something very highly non-trivial. So, but we don't think this is necessary in this case. We observe that first, the single qubit terms in the Hamiltonian that are the sum of zi's can be absorbed into initial state preparation, so that our initial states actually need to be plus and some phi prime 0, which is another product state that is also easy to prepare. So in this case, we only need to consider the two qubit terms, the sum of zi's, j's. We have a very important observation that this lattice with this interaction is two colorable, meaning that we can give every qubit in the 2D lattice a color which is either black or white, so that every ZIZG term in the Hamiltonian involves one qubit from the black color and one qubit from the white color. We also observe that if we sandwich each ZIZG term with one of the xi, where I is one of the IOJ, then we'll get negative of ZIZJ. So this gives us a very straightforward idea of preparing the history state. We can add some Z0 gates acting on only one color of the lattice before and after the ZZ evolution. So by doing this, we'll be able to produce the direction control state, which is as shown below, bottom here. So the zero is corresponding to like negative time evolution, and 1 corresponds to positive time evolution, and we just need to run another like a half time positive direction evolution. We'll be able to get like 0 and find out plus 1 and e to the minus IH on find out. That will be the history state that we want. However, in this case, we need to perform the C0 gates on a highly non-trivial half of the lattice of the qubits, because they are not just left-hand side qubits run C0s and the right-hand side does not run the C0s. It's like every color, no matter it's blue or it's black or white, they are everywhere in the system. So they may be hard in practice. It's too non-trivial. And we come up with an easier solution, which is based on a global CZ gate and some single qubit Hadamard gates before and after it. So if we do this on the qubits that we wish to run C-nodes on, we will be running C-nodes on these qubits. So the global CZ here stands for CZ gate that is controlled by the clock qubit, but has a Z operation acting on every other qubits that are the simulator qubits. Now, sorry. So this figure just shows the circuit that we want the prover to run, which is, well, just contains the Hamiltonian evolution for twice, global CZ gates for twice, and some Hadamard gates, and some measurements and initial state preparation. So now let's think about how to implement this circuit on some realistic devices, or the experimental implementation proposal. So we can see that our strategy shown in the last slide requires several types of quantum capabilities, including what we call this mode of computation a mostly analog commuting plus global CZ. So that's obviously harder than just analog commuting Hamiltonian simulation, but we think it's not too hard. So this includes performing a unit-time ZZ-type commuting Hamiltonian evolution twice, and running a constant number of single qubit rotations for each qubit, which will be just 4 times, and applying a global CZ gate twice. You can see that the first 2 capabilities are available in many different platforms, triple ions, neutral atom arrays, and superconducting qubits. But the global CZ gate part is obviously more challenging. So we have 2 candidate schemes to implement it. One of these is BOSS scheme, the other is related to the reconfigurable atom arrays. Let's see, what is the BOSS scheme? In the BOSS scheme, we want to use a single global BOSS degree of freedom. For example, it can be a qubit or a bosonic mode to implement the clock qubit. And the BOSS mode must interact strongly with each of system qubits, so that a single excitation or very few excitations in the BOSS mode can produce a significant effect, which will be a Z operation on every other qubit. Also, we need the coupling strengths to be in the strong dispersive region. And this kind of interaction is typically only achievable in superconducting qubits coupled to microwave cavities. But alternatively, there may be some implementations in vibrational modes of an ion trap. We also noticed that the entire simulator, that are the N qubits implementing the ZZ plus Z Hamiltonian evolution, must be inside or attached to a single BOSS cavity. And this feature is entirely possible to be implemented, but it needs to be incorporated in the initial design of the physical platform, meaning that we might not be able to implement this whole experiment on an existing platform, but we might need to design this platform from scratch, design this physical experiment from scratch. And an interesting thing we also want to mention is that there's recent exciting result related to this reconfigurable atom array. This atom array supports some parallelizable CZ gates. And so this allows us to run some kind of global CZ gates. But we also need to mention that their platform is capable of something more than just mostly analog plus global CZ. They're actually quite digital, so they're quite powerful. So this means that experimentalists doing reconfigurable atom arrays may be less interested in running our protocol. But anyways, we think there's a very straightforward idea of implementing this whole experiment using this atom array based on preparation of a GHZ state and using the parallel control Z gates to implement our global CZ gates. But the hardest point of this idea is that the GHZ preparation may be hard, because in order to do that, you need a sequence of C-nodes or some interleavings between quantum and classical operations. Therefore, we propose a multi-step solution where we first prepare a 1D square root n qubit GHZ state, and we apply the transversal CZ gates row by row by moving the GHZ qubits from the first row to the second row and to the square root n row. So as shown in this figure, those grid dots represent the GHZ qubits, and you can move them because this movement of qubits is a key feature of this reconfigurable atom array platform. So even though, as I said, this platform is capable of something much more digital, much more powerful than our protocol, we still claim that our protocol may be useful for them, because first we can, running this protocol can give some quantitative performance measures, which are the input and evolution fidelities. Also, we can help them benchmark their system in a sample efficient way. There's a summary of comparison, but in the interest of time, I may skip it, and we can discuss it if after the talk or if we have more time. So I want to move on to the discussions and outlook. The first question you may be interested in is that in order to demonstrate quantum advantage using this protocol, how many qubits do you need? So the bad news is to achieve the same level of hardness for classical computation as existing quantum supremacy experiments, we might need something like more than 3,000 qubits, which is crazy. But we also have good news, which is if we do some kind of trade-off so that a non-uniform H, so that the Hamiltonian evolution implemented in our system has some non-uniform coefficients in front of each ZZ and Z terms instead of just the same pi over 4. Then in this case, only roughly 60 qubits can be sufficient because it's the same number as their experiments. So we call this a trade-off between the hardness of implementing the Hamiltonian evolution and the number of qubits, because obviously non-uniform Hamiltonians will be harder to implement than uniform ones. Another question is, you might ask, how much noise in these measurements can be tolerated? Actually, the noise rate needs to scale as like 1 over n, where n is the number of qubits. This is like some kind of standard requirement, but it's not very easy to implement in near term. But we want to also mention that it can be as high as like 1% if we just use the trade-off here to apply this non-uniform Hamiltonian evolution. So 1% sounds like something totally acceptable in existing devices. Finally, we have some future directions. It would definitely be exciting if someone can implement these experiments, no matter it's on a mostly analog platform or on a purely digital platform like reconfigurable atom array. And we are also interested in some theoretical questions like, can you do some simpler verification schemes for some more general quantum simulation rather than just this commuting ones like ZZ plus Z's? Can we do this verification for some more general ZZ, like ZZ plus X times of Hamiltonian evolutions? So that's like an open question that we need to think about. With this, I want to conclude my talk, and thank you very much for your attention.
Great. Yeah, thank you so much, Zhenning. Do we have questions?
Yes, it's because this is actually related to something called security parameter. Well, if all the coefficients in front of the ZZ and Z's are the same, then there is an algorithm, a classical algorithm, to generate the samples in time that is exponential in square root of n, where n is number of qubits, so square root n will be that time complexity. And in order to compare with other like quantum superposition experiments where they need like exponential of n, we need our square root n to be same as their n. So in their case, their n is 60. Our square root n will also need to be 60. So n will be like 3,000. But if the coefficients in front of this ZZ and Z terms are non-uniform or somehow arbitrary, then we don't know any classical algorithm that can run in exponential of square root n time. So we would believe that in this case, classical simulation will take exponential of n time. So the n will only need to be the same as 60. So this can help us reduce. Well, I'm not sure about this. I think as long as it's not just uniform, we don't have the algorithm. But we haven't proven that like what kind of random, what kind of arbitrary will have this good feature. That's like another question.
Any more questions, Michael?
Well, I think IQP is necessary is because we want to have this highly efficient verification scheme, which is based on the estimation of the value of this 010 operator. And if it's not IQP, so you mean that would be more efficient, like as efficient as this? I mean, why this doesn't generalize to non-commuting?
You have to simulate the evolution, no? To do fidelity estimation with classical shadows.